the bottom button is going back. Okay. All right. So I will share with you some of my perspective on what I think are important applications and open problems in string field theory. So I will begin by recapping the formalism a little bit, just so that we're on the same page as to what we're talking about. Yes. So the closed, so Ted was mostly focused on the open string field theory in his talk. The closed string field theory, both the classical and quantum version of it, in the bosonic string context, was formulated in the seminal work by Barton Zwiebach in 1902. And as Min-Jae had already recapped, the recipes of this formulation are the following. So first, you have to define the space of string fields. The space of string fields, what they call H hat, is a subspace of the worldsheet, quote-unquote, Hilbert space, a slight misnomer. It's just the space of states of the matter sector of the worldsheet CFT tensor with the space of states of the BC Go system. The string field psi, which is living inside H hat, is generally completely off-shell, except that it's subject to constraint that has to be annihilated by this combination of B0 minus B0 tilde and L0 minus L0 tilde, as Min-Jae had already mentioned. One can then formulate an action functional in the sense of the BV formalism of the general form. This looks where this QB is a BRT operator and so forth. And this string bracket, which is some symmetric and linear map on the string fields, on the space of string fields, is the string vertex, the endpoint string vertex, which Min-Jae had already discussed. It based on general nice properties. So roughly speaking, as follows. The string vertices can be constructed in a way that's a little bit analogous to endpoint string amplitude. The recipes are that you have some correlate of the worldsheet CFT with some insertion of the string fields, which are analogous to vertex operators, but they're completely off-shell and subject to condition that already mentioned in the previous slide. You have to choose some coordinate maps, what they call Fi. And there's some insertion of BGOs, which is very similar to the usual prescription of on-shell amplitudes, but with some suitable generalization. And this integration is typically performed over a suitable domain in the moduli space of n-puncture Riemann surfaces. For the level classical string field, it will just be this n-puncture sphere, but there's a suitable extension of this to include higher genus contributions as well in the formulation of quantum closed string field theory. So for example, here I give a picture of schematically portraying how this quantity is defined. So here you got the 4-puncture sphere. At each puncture, you're supposed to insert the closed string field with a specific coordinate transformation that defines the conformal frame. There's some suitable insertion of BGOs, B and B tilde here. But this thing is supposed to be integrated over this purple domain within the moduli space of the 4-punctured sphere that you have to choose suitably. And as Min-Jae had mentioned, the part of this moduli space that's not covered by this vertex region, which I denote by gamma 4 here, are actually going to be covered by Feynman diagrams made out of other vertices, the cubic vertex in this case. And you can formulate a string field path integral in the BV formalism by a suitable gauge fixing procedure, which amounts to choosing a Lagrangian subspace of this space of string field H hat. Okay, so that's a very quick recap. Now, some frequently asked questions. Is the action unique? Far from unique. But the different consistent choices of the action or the string vertices are supposed to be related by field redefinition. So in that sense, it is supposed to be unique up to field redefinition. I'm not going to go through all these pictures here. These are for discussion later if someone asks in more detail. So do the different background worldsheet CFTs define equivalent string field theories? Ted had already mentioned this. To define string field theory, you have to have some worldsheet CFT to start with. And if you have a different background CFT to start with, you have a different string field theory. The action will be different. But we expect that they are supposed to be, again, related by theory definition, and it has been proven in the important series of papers by Sen and Zwiebach in the 90s in the case of infinitesimal marginal deformations of the CFT. Is the closed-ring field theory more than just perturbation theory? This is a question that has also come up during Min-Jae's talk. I would say not obviously, but I'll come back to this. It's quite possible, at least at the classical level, that the perturbative series with vector string field may very well converge for suitable observables of interest. And a complaint you might have with Barton's original formulation in the context of bosonic closed-string field theory was that isn't the bosonic closed-string field theory ill-defined at the quantum level? Yes, for the usual reason, the closed-string tachyon, unless the worldsheet matter CFT admits no normalizable relevant operator, which will be the case, say, in the C=1 string theory, the 2D string theory. In that case, it is perfectly, it's expected to be perfectly sensible at the full quantum level. But now let's come to the superstring field theory. It took a while, as you can see, the closed superstring field theory, both classical and quantum level, was completed by Ashok Sen in 2014. The new ingredients that go into this, in addition to the recipes that I have already mentioned in Barton's original work, includes the following. So now, in order to define these string vertices, not only you have to choose these coordinate maps, but you also, together with the domain over the integration over the moduli space, but you also have to choose the location of the picture-changing operators. And there's an important prescription of vertical integration, which Ashok had formulated, that allows you to get around this issue of spurious singularity that had been pointed out in the late 80s and had bothered experts for 20-something years. The space of string fields now is defined similarly to the bosonic string case, except now you have to deal with NS and R sector, respectively, on the left and on the right for the type 2 string. And then one is instructed to always work in the -1 picture in the NS sector and -1/2 picture in the Raman sector. Note that the algebraic operation one will perform on the space of string fields are the string brackets, which are closely related but not the same as OPEs. So you do not need to demand these things close under OPE, anything like that. The first important application or serious application of this is it gives a complete formulation of superstring perturbation theory, as it was laid out by a series of papers of Ashok Sen from 2014 to 2016. And these are there are two nice reviews of this. The outstanding review just appeared last week by Sen and Zwiebach. It's 170 pages long, which I highly recommend. So what does it do? Well, by construction, these vertices are going to be finite by the choice of these integration domains. It's going to be free of UV divergences, and in particular, there's also a natural prescription for the momentum integration contour, which is specified by any continuation from Euclidean green functions that was explained in the paper by Pius and Sen in 2016. It provides a systematic treatment of mass renormalization in string theory, string perturbation theory. For instance, if you want to calculate in SO32 heterotic string theory, there's like this heterotic particle in the spinor representation of SO32, and the mass is, there's unambiguous G-string correction to its mass. And to do that systematically, one would like to work in this formalism, which treats scattering amplitude in the same way as in perturbative quantum field theory, that is, you work with you work with amputated Feynman diagrams and so forth. It provides a systematic treatment of massless tadpoles. Massless tadpoles can lead to a breakdown of perturbation theory, but in ordinary perturbative quantum field theory, or ordinary quantum field theory, if you encounter this in perturbation theory, you will conclude that the massless tadpole contributes to the effective potential of some, say, massless scalar field by a linear term, and that leads to a shift of the vacuum. Even in a situation where the massless tadpole cancel, which is familiar in string theory, this cancellation mechanism very often, typically, requires canceling contribution to, say, string amplitudes that involve different components of the moduli space of the worldsheet surface of different topologies. And a priori in that situation is not, even if when the divergence cancel, in order to get the correct finite piece of the string amplitude, you have to choose cutoff schemes on different components of moduli space in a consistent way. And the string field theory provides a consistent procedure, a systematic procedure for dealing with that. Now I will discuss some further applications of string field theory. So one is to describe the general string backgrounds. So Min-Jae's talk has already covered the subject of superstring Raman flux background. I would say that to the extent we understand in the usual RNS formalism, which is based on a superconformal matter CFT coupled to BC beta gamma system, if you turn R flux, it's generally expected that this matter CFT is deformed into something that's not a local CFT anymore. Perhaps in some other formalism where you introduce some additional ghosts, like in the pure Spinner formalism, one can find some non-unitary local CFT to describe this, but at least within the RNS formalism, we wouldn't know how to do that. Nonetheless, one can begin with a NS-NS background, which has a worldsheet CFT description, and in which you can then define a closed string field theory. Here, I'm going to describe the equation of motion as opposed to the action, which is sufficient for this current discussion here. So the equation of motion will take this form as it's going to follow from the action I wrote earlier. It says QB acting on the closed string field is something that involves this object known as the string bracket. The string bracket, as was also played a role in Min-Jae's slides, is related or unique, unambiguously specified by the string vertex that was defined earlier. It's not associative, unlike the star product that Ted had mentioned, but it has some important L infinity structure, at least at the level of classical closed string field theory. So now, given this, the string field that's supposed to obey this equation, if you start with some background CFT describing some NS-NS background, you can now look for string field solution that describe turning on, say, R flux. So this was the subject of Min-Jae's talk. I guess all three examples was he has mentioned already. A second potential application is to time-dependent background. Now, in this case, I would say that we have an incomplete understanding of what we're supposed to do with the worldsheet CFT. In a situation where, following the usual recipes, you expect the worldsheet CFT to come out of a nonlinear signal model with a Lorentzian target space-time. But if there's non-trivial time dependence, the weak-rotated version of the target space will lead to a complex metric and a non-unitary worldsheet matter CFT. This weak rotation procedure is very subtle. There's a precedence of some understanding of this in string theory, which is for time-dependent open string background. That is, the open string rolling tachyon describing the time evolution of open string tachyon on unstable D-brane. So this was explained by Sen in 2002, where one can try to construct a boundary CFT description with a time-dependent open string background, but some very subtle continuation is required to make sense of that. Now, in string field theory, in principle, this is straightforward to describe, at least within perturbation theory. All you need to do is to turn on a non-trivial time-dependent string field solution you can construct perturbatively, using the same kind of procedure that Min-Jae had described. Now, I think the challenge here is really just to carry out this exercise in interesting cases to identify and determine physical observables. So there's a small exercise we carried out in the paper from last year, where in the open string field theory, we studied the rolling tachyon as a perturbative solution and computed its energy using the covariant phase space of the open string field theory. I'll come back to the discussion of these observables, of other observables, maybe toward the end. A second application is the study of D-instanton effects. So D-instanton effects are non-perturbative effects in string theory of order e to the minus 1 over G string, which are supposed to be captured in the usual description by some boundary CFT, which correspond to some boundary condition of a D-brane localized in both space and time. So here's a heuristic picture. So in the worldsheet, you're supposed to think of the D-instanton as a boundary condition. In the space-time, is this dot look like this, and you're supposed to compute this kind of amplitudes and integrate over the moduli of the D-instanton, and that's supposed to be a non-perturbative correction to a string amplitude. At least that's in the usual kind of naive, following your nose on-shell approach. And so in particular, in this a few years ago with Balthazar and Rodriguez, we indeed attempted that in C=1 string theory for the ZZ instanton. And while the results were mostly working and agreed with the matrix, dual matrix model in the highly non-trivial manner, we did encounter some ambiguity, which is that there's some, this is similar to this issue of the massive tadpole I mentioned earlier in perturbation theory. So here, there's some different worldsheet topologies that will contribute to the D-instanton corrected closed string amplitude that requires cancellation of divergence from different diagrams of different topologies. While it's easy to understand the divergence will cancel, this was actually already explained by Polchinski in '94. To get the finite part right, one has to choose some consistent prescription for cutting off the moduli space of this Riemann surface on the left and this other Riemann surface on the right. And it's not obvious how to choose that. And so you need to choose some kind of consistent cutoff. And this was explained by Ashok Sen in the following year with the so-called D-instanton perturbation theory. It offers a first principle approach to D-instanton effects based on open plus closed string field theory. That is, you have closed string fields in the bulk and open string fields on the D-instanton. So the ingredients are the following. The new ingredients are the following, in addition to the closed string field theory I have described so far. So here we are instructed to so here this SOC stands for the open closed string field action with open string field psi open on the D-instanton and the closed string field psi C in the bulk. If you integrate out the open string fields, you're supposed to produce a correction to the closed string effective action. That's how you would compute, in principle, the correction, non-perturbative correction to closed string scattering amplitudes. It turns out the Siegel gauge is singular, importantly, and one has to replace that with the gauge, which we now refer to as Sen gauge. This approach has passed highly non-trivial checks in the context of C=1 matrix quantum mechanics, against C=1 matrix quantum mechanics for the ZZ instanton in C=1 string theory, and also against also in type 2b superstring in 10 dimensions, it was checked against non-trivial soft dilaton relations. And another subtlety is that this open string field patterning rho here, the integration over the so-called massless modes have to be performed non-perturbatively, which kind of is the string field theory analog, or rather replaces the idea that you are supposed to integrate over the moduli space D-instanton. So the correct way to do that in string field theory is to integrate this massless open string fields modes non-perturbatively. So this has been extended further. In fact, I forgot to mention here that the extension of this in a beautiful series work to the instantons in minimal string theory will be discussed later today by Raghu. It has been extended to a multi-D-instantons in type 2b string theory, to wrap D-instantons in type 2 string theory combined on Claviel spaces, and so forth. Let me just mention that a major challenge that remains is to understand how to handle the open string field integration contour in general. Maybe I'll skip this picture for now and leave this to discussion later. A third application is to understand quantum string vacua. By quantum string vacua, I mean the kind of string vacua whose properties can only be understood when you take kind of quantum effects. So an example of this was already mentioned in the very nice review by Miguel yesterday. So in 10 dimensions, there's this non-supersymmetric SO16 times SO16 heterotic string theory, which is known to, you formulate this theory starting with Minkowskian target space time from the worksheet CFT description. But it is known that there's a one-loop contribution to the vacuum energy density. So there's one loop contribution to the cosmological constant. That means the Minkowskian space-time is actually not a solution. And so you have to, in order to understand the actual vacuum, or as admissible solution of the theory, you have to move away from this Minkowskian space-time. In the past, this has been always treated from the effective field theory point of view, but a systematic treatment that takes account of all the stringy effects into account would require string field theory. Now, this specific example, as far as I know, has not been worked out in the string field theory framework, but other similar examples has been studied. So, for example, thank you. For example, it was known for a while, since the work of Dine, Seiber, and Witten, that if you compactify SO32 heterotic string theory on the Calabi-Yau space with a standard embedding, there's a one-loop via Iliopoulos term that's generated, describes some effective potential like this. What it means is that you have to, the naive vacuum is unstable. You have to move to a true vacuum. And this is described in the work of Ashok Sen in 2015 by constructing the explicitly, perturbed string field solution that described the shifted vacuum in which supersymmetry is restored. Now, there's much work to be done in this area. So one avenue for future investigation is to consider string field theory solution of the kind of the type that Min-Jae had described in his talk about that described fluxing education, but importantly with the D-instanton effects to account. And these D-instantons could be wrapped on the internal space. And if you have a vacuum solution that relies essentially on the D-instanton effects of the wrapped D-instantons, and if you want to have a fully 10-dimensional description, then this is certainly almost not possible to describe this within the standard 10-dimensional effective field theory framework, almost kind of by definition. But I think with this open plus closed string field framework for treating these kind of effects, this should be possible. And then there are important questions of whether the string field theory can capture other non-perturbative effects, such as NS5 brane instantons, maybe as non-perturbative saddles of closed string field theory, and how to deal with things like other non-perturbative effects, like the gauge condensate in the context of KKLT, which are understood to be important for the existence of certain non-perturbative vacua. Let me comment on some additional future prospects. One issue which I had mentioned already is whether we can complete the closed string field theory at the classical level. Even at the classical level, the closed string field action as it's formulated is defined as a formal power series in the string field. But it seems to me that there's no fundamental reason why one cannot sum up the series. There's some evidence that this can be done because we can try to construct string field solutions that describe deformations of CFT where we already know where the endpoint is. So in this recent paper, for instance, it's from the March of this year, the solution that's dubbed the tachyon dilaton eschatology solution describes a string field solution that involves turning on a tachyon profile in one dimension of this red shape, and also a dilaton profile of this purple dotted shape, such that the solution actually blows up at some finite but large distance. At the end of space, there's so-called Runkel-Watts wall. But it turns out that this whole thing describes a deformation of the worldsheet CFT that's equivalent to replacing, roughly speaking, a free boson by AK minimal model. So where this 1/k is, roughly speaking, the expansion parameter of the string field solution. So in this case, we know the endpoint is just a minimal model, and it ought to be possible to sum up the perturbative expansion in the string field, even though the solution so far we have only understood it to some at a perturbative level. Strictly speaking, away from the wall where the solution blows up. This leads to the question of what is really the space of admissible string fields, because this thing naively it looks like it's kind of bad because the solution blows up somewhere in a large distance, but it's clearly good because the endpoint is a sensible CFT, and that's what we want. In fact, I think for reasons that maybe I'll leave to the discussion, to understand this more generally, the precise realization of diffeomorphism as an L-infinity gauge transformation in string field theory will play an essential role, in particular to understand how you can start with one background, turn on a string field solution that changes the topology. Thank you. Another future perspective is this question that's been around for quite a while. Does open string field theory, so I emphasize the word open here, open, does open string field theory make sense at the quantum and at the non-perturbative level? There's some indication that the general or heuristic reasoning why you might think this should be possible. First of all, the D-instanton effects may well be understood via non-perturbative saddles in open string field theory, goes like e⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ open string loops can cover the multi-space Riemann surfaces with boundary, like depicted by this picture here. I think the simplest test case would be just to apply Witten's cubic open string field theory, as Ted had described, literally in that form, which is applicable to ZZ branes in C+1 string theory. I think most of you know this Fermi C picture of the dual of the matrix model dual to C+1 string theory, and we expect the ZZ brane to be dual to a single fermion. Now, it's expected that sort of heuristically, roughly speaking, the open string tachyon potential to look like this. It has a shape like this. The right side of the potential is where the tachyon condenses into the closed string vacuum. This was the Schnabel solution that Ted had reviewed earlier. And if you look at this picture, this thing looks like the profile of the matrix quantum mechanics potential, but up to the Fermi surface. This open string field theory has got to know about the Fermi surface, and it cannot be that it's just a free fermion. And perhaps also know about other fermions, because this open string field theory has this double brane solution that Ted had also just described. So I think the full story is yet to be fully, there's some pieces of the puzzle that's yet to be sorted out. And we'd like to understand whether the open string filter on ZZ brane is fully sensible at the quantum and non-particular level, and whether it can reproduce this entire, the experience of the fermion in the presence of the Fermi sea. In practice, how would you proceed? Well, one possible approach is to study time-dependent perturbation theory of the perturbative open string field theory around the rolling tachyon background. Another possibility is to define the open string field theory path integral non-perturbatively directly, perhaps with some suitable regularization scheme. Okay. And this is my last slide. Another possible future prospect is to try to understand open-closed duality as a field redefinition, open-closed string field theory. So in the 2009 paper that Minjae had already mentioned, there's a way to formulate open plus closed string field theory in a two-parameter family, labeled by these parameters LO and LC, that represent sort of the color width or circumference of the open and closed string punctures. Now, these are just some parameters you can use to define some two-parameter family of different open plus closed string field theories that are related by field redefinition. The point here is that in some limits of this chart here, we have some mostly closed string field theory, and some other limit that has some mostly open closed string field theory, and they're related by field redefinition. So you might want to realize open closed duality simply by this kind of field redefinition. And one testing ground of this is the rolling tachyon, as I was mentioned on the previous slide. You may also try to more ambitiously, following Huang's original philosophy, derive holographic duality by the two-step process. First, you derive open-closed duality as a field redefinition, and second, you take the decoupling limit. It seems to me that actually taking the decoupling limit is one big conceptual challenge here. I mean, the idea here being that you might start with open plus closed string field theory, just describe a flat D brane probing some flat space-time. I mean, there's nothing wrong with that description. Now you can perform a field redefinition, which is roughly speaking kind of like integrating out the open strings. And it produced nonetheless some source for the closed string, and you can try to solve the closed string in the presence of that source. And you find some non-trivial closed string field solution, which I heuristically depict by this very schematic picture. And the challenge is to really to recognize that it has a horizon, and you can take a near horizon limit. I think this requires understanding more carefully how diffeomorphism is implemented as a gauge transformation. So I'll stop here. Thank you.
Now the floor is open for questions. Yes, Kamran.
Thanks for a nice talk, G. So for closed string field theory at one loop level, for no insertions, how does modular invariance come out from string field theory?
I think the current formulation always requires some insertion. But the thing is, you can in some sense, it kind of captures the coupling dependence through the insertion of dilaton. But the way it's currently formulated, I would say it always requires insertion. Let's say if you want to solve for the correction to the background by taking kind of a one-loop contribution to the cosmological constant, what you actually do is it's like essentially varying that with back to dilaton, you get some vertex with some dilaton insertion.
So you will miss the constant term.
That's right. That's right. But I think you'll nonetheless get a correct result at the end, even though you don't have this explicitly in the action.
No, I mean you cannot fix the constant this way.
That's right. Yes.
Okay,
yes.
Thank you.
But the constant is just one point function of the graviton, right? Or the dilaton. So the constant is not really relevant for string field theory.
Constant is not? What do you mean?
I mean, what you normally think of as cosmological constant is really the 1 point function of the graviton, right? Because it's lambda times square root of determinant G. And that's how you detect the cosmological constant.
No, the vacuum energy diagram, just the particles you just trace up Q, the L0, L0 bar that becomes.
Yeah, well, that's not physical in string theory. But if you think in terms of effective action, right, the effective action which captures cosmological constant has a one loop, has a 1 point graviton function. So that's the way you determine cosmological constant.
Well, you can put, there's a volume, there's a...
Yeah, exactly. So in the theory of gravity, if you just add a constant to the action, nothing changes.
No,
right?
by constant, of course, we mean the covariant.
Yeah. So that will also give rise to graviton 1 point function, and that you can detect.
That you can get. How does the modular invariance come out of that? How does the modular invariance get implemented?
I think it's basically built in the formulation of string field theory. Because when you cover the moduli space, you make sure that you cover it only once.
But if it is, the reason I'm asking this is that the question I was asking from Minjae was related to this. Modular invariance would know about winding states. So if it's already baked in, it should have known about winding states. How would it not be knowing? So when you go, or the orbifold constructions, the twisted sectors come from modular invariance. If it's baked in, why doesn't it know about twisted sectors?
But if you start at r equal to infinity, it will not know, right? If you start at any finite r, it will certainly know about winding states.
So like if you quotient out by Z3 transformation of R2, how does the twisted sectors come from modular invariance in string theory? If modular invariance is built into it, why doesn't string field theory know about twisted sectors? My question.
I think you see, you can in string field theory, there is no notion of quotienting. I mean, it doesn't give a simple string field theory. What you can do in principle is that start from a conical defect and then try to blow up. That you can study using string field theory. But the quotient, I mean, what you are asking is that if you start from string field theory in a flat background, can you quotient it by some Zn group?
Like discrete gauge symmetry.
Yeah. So that doesn't have a simple description in string field theory, as far as I know.
Okay,
I don't know, one of you can add.
Maybe I'll just add to that. I mean, you could try to ask whether starting from, say, a flat target space, you can turn on string field solution that kind of, that closes it up, right? In the case of circle communication, I do not actually know how to do that. But there's another situation which I think I kind of do know how to do that, at least partially, which is that you can turn a R3 into S3. So in that case, of course, you require turn on H flux, as we know. And we know from the WZ model description what it would look like if you just take the S3 non-sigma and just expand in one over radius. Now, from the string field theory point of view, one should be able to write down a perturbative solution at the very least that describes the 1 over radius expansion. Now, the key is going to have to do with the kind of summing up that 1 over k expansion. For example, from this point of view, it's not obvious why k would be quantized and things like that. I think I was mentioning earlier, I think this is where the diffeomorphism will play a key role, because in the string field theory description, as Min-Jae has mentioned already, there isn't a patch-by-patch description. So if you want to describe this S3 solution, it's a little bit like this eschatology solution that is going to look regular for some, it's going to look regular for some large region of space, but then the solution is going to blow up somewhere. But in the case of the S3, we know that if you go to the different gauge, it should look regular in that place as well. So I think, by thinking about the diffeomorphism, one should be able to recognize the full S3.
Okay, thank you.
Okay. Yes, go ahead. Yes. I think you can press the button there.
Okay. Yeah, okay. Thanks you for the nice exposition. I was wondering, you mentioned some systematic way of dealing with March normalization, stuff like that.
Dealing with?
You can't hear me? You mentioned a systematic way of dealing with some kinds of IR divergences. So I was just wondering if there's a systematic way of dealing with other kinds of IR divergences, like due to soft photons or things like that.
Oh, well, maybe Ashok would.
Yeah, dealing with what?
With other kinds of IR divergences due to soft photons.
Yeah, so I think whatever you can do in quantum field theory, in Potter-Besson theory, you can do using string field theory. So if you are thinking of the IR divergences that come in QED, for example, yeah, so you can certainly use the string field theory to deal with those.
And is there like some equivalent to Fadeev-Kulish you can use?
Some equivalent?
Something equivalent to Fadeev-Kulish you can use from string field theory?
Oh no, Fadeev-Kulish I don't know how to understand from string field theory. This is purely as a perturbative statement. That if, for example, you want to describe some inclusive or semi-inclusive cross-section, that you can do in string field theory.
Okay.
Because you have the standard LSG formalism here.
Okay. And can I ask a clarification? Sorry, when you mentioned the time-dependent background, and you talked about the usual issue of weak rotating and stuff, in string field theory, you didn't have that issue of...
Well, you see, in string field theory, we never deform the CFT explicitly. We always work in the original CFT. If you start with the static background, that's the CFT you're committed to. The string field lives in the space of states of that CFT. So the time dependence just had to do with what is the string field profile you turn on, but that profile is just some state in that vector space.
Oh, that's cool. Okay, thank you.
Okay, yeah.
Yeah, hi. So I would ask a slightly higher level question. So certainly I'm happy with string field theory as a sort of perturbative approach. If we want to try to, as you were saying, complete it or something, I guess I get a bit confused because I thought the modern understanding of string theory is that it's not a theory of strings. And so, for example, like if you try to discover QCD by being very careful about quantizing the chiral effective action of pions, it seems like that would be a hopeless endeavor because you're not going to see the quarks and gluons there. You need to find the right degrees of freedom. So I don't know. Yeah, how do you think about that?
So I would say that, first of all, exactly what are the right fundamental degree of freedom could be a matter of taste. But one could focus on a more concrete goal of asking whether you can get some observable exactly right. One possible approach is to say that, say if I want to obtain the exact number S matrix of type 2B string theory in 10 dimensions, Minkowskian, asymptotic Minkowskian background, I have perturbation theory, I might want to add D-instanton contribution, add NS fiber instanton, and if I can collect all these contributions, I have, I'm careful with the left-share symbol and all that, maybe I can put them together and get a full answer. That's one possible approach. Now, of course, in general, I don't see any obvious reason why the closed string field path integral by itself can be made non-perturbably well-defined. This D-instanton perturbation theory is a somewhat strange object from the quantum field theory standpoint, right? Because we're adding the D-instanton effects as additional open string sectors. It's not saying that we're finding a solid point of the path integral of the closed string field. On the other hand, as I was mentioning, the open string field theory, on the other hand, there's a chance that that could be made sense non-perturbed by itself. So I think these are all interesting avenues of investigation, but I don't have you know, I cannot really comment on what the final story would be. Maybe if you want to add.
You have something to say? You want to add?
I guess.
Do you need the?
As far as I'm concerned, I think one can also take the point of view that one of the lessons of dualities is that you can have many different coordinate systems on your theory space, and some coordinate systems are more effective for certain types of physics, and there may not be a single fundamental set of degrees of freedom that somehow describes all of string theory. It's just a philosophical point.
Oh, actually, I have. I have a related comment to that. Actually, also related to earlier question. I think that asked during Minjae's talk about the back reaction of the orientifold. There are different descriptions of the same system, say, or a string vacua, depending on your effective description and what you keep to be what you choose to include in your effective field theory, and depending on, let's say the Wilsonian cutoff or whatever, the solution could look quite different. So, for example, in the open classical string description of some D-brane in some probing some space-time, the back reaction is not put in to begin with. It's outcome. If you calculate the amplitude, you already knows about that back reaction. This is different from the supergravity description of the D-brane, where the back reaction has to be counted as part of the supergravity description, but you don't do that in the string field theory. So I think related to this, I think there's a kind of a way of thinking which is kind of predominant in the 90s, where we would like to say that at weak coupling, we would like to use the D-brane with boundary CFD as a description. At strong coupling, we move to supergravity. But the whole point, I think, one of the biggest lessons of ADS-CFT is that you should be able to do both simultaneously, and they're both valid description in an overlapping regime. And open plus Gaussian field theory would allow you to somehow do that to some extent.
So maybe one other thing I can add is that in the context of the proof of background independence in open string field theory that I sketched, there's never an open string field theory that is somehow the fundamental one. There's just all of these open string field theories, and you can choose one. And if you choose one, you can describe any other and go to that other D-brane and then go back, and there's somehow there's never like a fundamental description. There's just many descriptions and their transformations between them. So.
Go ahead.
Yes, so regarding your fantasy about deriving open closed dualities, let me recall a little toy model we studied with Davide Gaiotto long ago. Admittedly, it's in terms of topological strings, so you start from the open string field theory on FCCD branes in the C2 theory, and that seems to work to the end. Of course, admittedly it's a toy model, but nevertheless it does work. You get the Concierge model, which is fully non-perturbatively defined and gives you the definition of the theory. And perhaps you could try to play your open closed game in that context.
Thank you. I should have included that in my slide. I apologize for omitting that.
Yes, go ahead.
Yes, I have a question for the three of you. Regarding tachyon condensation, in the old days there was this issue that when you have a brane and anti-brane annihilating, you had two U1s, but the tachyon is only charged under a combination of the two. And the question is what happened to the leftover U1? I remember, Ashok, at some point you were saying there should be a confining field, gauge theory, but do you have any understanding now?
What's the issue?
Yeah, that if you take a brane anti-brane system, there is a center of mass E1, right, which seems to be unaffected by the tachyon condensation. So the question is, what happens to that E1, the center of mass E1?
Okay. Was that, I'm not sure I know that issue. What is the, so you have a brain-anti-brain, and
So the tachyon couples to the relative U1, but the overall U1 is insensitive to the tachyon background.
okay.
Right? So the question is, at the end of at the tachyon vacuum, what's happening to the overall U1?
Okay. Well, is this just a question of what the open string states that are existing at the tachyon vacuum? Right. So there, okay, for the superstring, okay, there are no open string states at the vacuum. So one can talk about how you understand that analytically, but is there more to this question, or?
I mean, I think that there is no Snabel type. Is there a Snabel type solution where one can explicitly see what happens to these U1s? It's a brain anti-brain system. That's right.
Right. So there's a tachyon vacuum solution on the brain-anti-brain system, which has been derived analytically, and you find that the spectrum of fluctuations around that solution is empty. So that is, and it works in a way which is quite analogous to how it works in Schnabel's solution.
But the question is that the tachyon is only charged on the one U1. So in field theory, how can you explain that what happened to this extra U1 that is not broken?
I'm sorry, I somehow am not understanding the question.
The tachyon is charged under only one of the U1s.
Uh-huh.
Right? The other tachyon is neutral under the other U1.
Okay.
But just because it's neutral doesn't mean that it would decouple, right? Maybe I'm also not understanding. Why would you say it would necessarily decouple? I mean, it can still couple in some very non-trivial way, just not minimally couple.
Well, you have two U1s at the beginning, and at the end, the tachyon only brings one of the U1s, so what happened to the second U1? From the field theory understanding, from the potential that you do, there has to be an explanation what happened to this extra U1. I think Ashok at some point you have some...
I mean, it will be good to check in this example, right? How both the U1s disappear. I mean, you are saying that they disappear, the cohomology is empty, but one should be able to maybe follow the two U1s.
Yes, okay.
Okay, I think there is a question on Zoom.
Yes. Can string field theory for a background with ND0 branes be useful to address the BFSS conjecture or BMN?
I'm not seeing what it can add to what, let's say, had been discussed by Juan earlier today. Well, first of all, the conjecture itself is about some kind of decoupling limit. So you don't. Or, I mean, is the question about to derive, or is it to derive some duality, or?
Well, I think I didn't ask the question myself, but I assumed. But yes, I assume the idea is whether some of this strong coupling behavior you can describe more effectively using string field theory, or whether it's all encompassed by this matrix model.
It's not clear to me that the string filter has anything to add to that.
So this is related to the previous question and also to some of the questions asked before by some people. So is there a way to see the well-known string dualities in the framework of string field theory, or at least some portion of it?
So, sorry, which duality?
String dualities. Let's say SL2Z duality in type 2B.
Well, for The superficial answer is no, there's nothing to be said so far because the closed string field theory is formally perturbative. Now, if you're talking about including the D-instantons, right, treated as open string sector, well, there are non-trivial tests of S-duality, first of all. But I guess at this stage, I would say that there's no arguments for something like deriving S-duality from this perspective, but all of its predictions concerning D-instanton corrections expanded in e to the minus 1 or GS. Some of it has been checked in a non-trivial way from the string field theory. When I say check, of course, I mean that in a situation where you can actually pin down the answer by superstring constraints together with SL2Z invariance, and so you can pin down the entire function on the fundamental domain of SL2Z, and then you pull out the tail in this expansion in e to the minus 1 or GS and compare with the D-instanton computation. I mean, a priori, otherwise, if you only compute some, let's say, some non-BPS protected D-instanton effects, there's no obvious way to test that against S-duality because you're just expanding around the cusp, and it's not like you're really testing against S-duality.
I mean, having an action never helps in testing dualities. Because, I mean, it's like, even if you write down the n equal to 4 super Young-Mills action, right, which is complete, I mean, it says nothing about S-duality of the theory. So I don't think that having an action is really useful for testing non-perturbative dualities. Yes.
So it's totally different direction, but I think one of the interesting application of string field theory can be understanding time-dependent background of string theory better. In the sense that within the context of worldsheet conformal field theory, we lacked criterion what kind of theories are admissible and what are not. So in the case of string field theory, if you look at the string field equation motion, do you think you have a well-defined set of conditions for which class of string field are admissible and not admissible if we want to study time-dependent solutions?
I think we understand very little about in general, what are the admissible space of string fields. I think even in the context of the open string field solution, that Ted was describing that correspond to deforming the boundary condition, that was still limited to unitary theories, more or less, right?
You mean the matter part of the CFT?
Yeah. I mean,
okay. Yeah, it would help to consider unitary CFTs, but I think the like the rolling tachyon solution, we looked at that also in the context of this construction, and it you can see some more things about it, like how the like for the cosine deformation, like how the solution looks like as you approach the critical parameter where the boundary state vanishes. So I don't know if there's any big issues there. I think one issue with time-dependent backgrounds in string theory is that once you leave the perturbative construction, if you're looking at time-dependent backgrounds perturbatively, you always know that you're starting basically a linearized order with a free theory with a well-defined initial value problem. But what happens is that if you start your fluctuation around your background becomes large, then you don't know how to systematically parameterize the solution space because there's no local action which allows you to set up initial conditions, at least in the covariant formalism. But in the light cone string field theory, there is actually a local action, and which in principle could be used to systematically parameterize the space of initial conditions in string theory, but I don't think this idea has been made use of in any significant sense.
I mean, just to add to that, I think the current formulation closed string field theory is a little bit like trying to do GR, where you just expand the metric around the Minkowskian metric, and literally do perturbation theory, right? I mean, you can do that perturbatively, and most space-time you like to describe will look very ugly, but nonetheless, you can try to carry this out, but it will be hard to go very far if you don't recognize the underlying diffeomorphism. And here, indeed, we do not have the patch-by-patch description, but I would hope that even without a patch-by-patch description, once you understand diffeomorphism well enough, it might be good enough.
So one of the most impressive parts of the, I think, at least to me, the string field theory that you discussed was tachyon condensation for open strings. Right. So the natural question is whether there's a closed string analog that has been studied. For example, the Adams, Polchinski, Silverstein closed string tachyon.
Yes,
have people studied it, and what is the story there?
So that was studied in, okay, the analog of that orbifold was studied for the bosonic string field theory back in the late 2000s by Okawa and Zwiebach, and they found some solutions, okay, but the problem with the closed string field theory, of course, is that it's non-polynomial, and they included the cubic vertex and I think some corrections from the quartic vertex, and they only included some like the tachyon, the closed string tachyon state, and it's a non-compact solution because the orbifold's non-compact, so one has to cut off the momenta of the states that you're keeping track of, and as I recall, it was a very crude approximation, but they were able to find something that is approximately stationary points that could be interpreted as a change of the deficit angle at the orbifold. But I think those computations would have to be improved by a lot.
Thank you.
I'd like to add to that, actually. So, I mean, the difficulty with that tachyon condensation study was that it's generally non-perturbative, and the closed string field theory is only defined, as a power series formally, and you don't really know for certain whether it will converge or not for this specific type of solution. But there have been other types of solutions which are conceptually very similar, but that's under much better control, which is just that you can use closed string field theory to study a short RG flow of a CIT perturbed by relevant operator, which was just done, I think I had a reference here by Mukherjee and Sen in '91, and we also revisited some related issues recently. So there, it's similar to tachyon condensation in the sense that you turn on a kind of a slightly tachyonic mode, right, correspond to a slightly relevant deformation. And you can construct under optimistic scenario where if the deformation of operator of safety is only slightly relevant, but its three-point function not too small, then you have a controlled perturbation theory, and you can indeed write down a corresponding, with some caveats, write down some corresponding perturbative controlled solution to the closed string field theory equation of motion, where the perturbation parameter would be how far you're away from marginality. So that can indeed be done. And in some sense, even this this thing here, this tachyon dilaton eschatology solution is kind of like tachyon condensation, where we turn on this oscillating tachyon profile, but the dilaton is also turned on, and there's some non-trivial endpoint which describe a deformed CFT.